All right, let's get started. Well, hi, Mom. Hi, Dad. And chapter 12, Solutions and Colloids. That's our topic today. So, say that again. It's off. How did it turn off? Oh, that happened. I see. It has the screensaver. No, let me see how to fix this. Great. I think it should be fine now. Let's see. And it is recording. Great. Let me know if it goes off. I'll see. This is the first time I'm doing this. I don't know how it's properly done. Okay, so solution and colloids. I will not be really talking about colloids that much. You just need like a qualitative understanding of what colloids are, just the definition and a couple examples maybe. All of the mathematics in this chapter will come from solutions. All right? So we'll talk about various solutions, various properties of solutions, and also how to measure the concentration, i.e. how concentrated your solution is, right? So first of all, what is a solution? Very roughly speaking, it's you have a liquid of some kind, and then you have some kind of gas or solid or liquid dissolved in that, right? So our solutions, for our sake, are going to be solids or liquids or gases in liquids. The thing that's present in the greater quantity, we call that the solvent. So for the purposes of this chapter, our solvent will be liquid. And the thing that is dissolved, i.e. the thing that's present in the lower amount, is the solute. So a solute dissolved in a solvent gives it a solution. So that's what a solution is. Right? So it's a mixture, but a very specific kind of mixture. The important bit about the mixture is that an important thing of a mixture, of a solution, is that the mixture be completely homogeneous. You don't want to see any separation of the solute and the solvent. So an example of a solution is salt dissolved in water, right? But a mixture of sand and water is not a solution because the sand eventually settles out, right? So you need a very homogeneous mixture. That is solution. Great. Now let's think about the process of dissolving one substance in another. So the process of dissolution. Dissolving one substance into another is called dissolution. Let's come up with a very simplified model of what dissolution looks like, right? Imagine you start off with your solute, consider it a solid, and some liquid, your solvent. Solute and solvent. So we're going to do very simple things, one by one, and get to the final stage of being a solution. Okay? One way to think about how a solution forms is to first think, well, going from here to here, what's the end story? The solute particles are all mixed in with these solvent particles, right? That's the end story. So let's do that in steps. First, you want to break up your solute. You want to expand your solute. So you take your solute in the condensed form as a solid, like think of this as an iced a sugar cube or something, and you want to separate out the sugar molecules or the salt molecules, solute molecules, whatever it is, or ions, if it's an ionic substance. So the first thing that you do is you expand the solute, and you keep the solvent unchanged. It doesn't matter, the order doesn't matter here. We could have expanded the solvent first, solute second, it doesn't matter. It's just, let's do this one by one. So this is the first step in the dissolution process. What's the next step? The solute is ready. The solvent is not. So let's take our solvent and also expand it. Separate out all the molecules of the solvent. And then the last step is to put these solute particles in the spaces that we just created within these solvent particles. Does that make sense? So these are going to go in and fill in the holes. And so at the end, you'll get your homogeneous solution. It's a very exaggerated separation. The separation is much tinier, but you get the idea. So it's a 3-step process. The second step here is expand solvent. Right? You expand the solvent. The last step here, just putting it in words, is form your solution. It's a 3-step process. Now let's look at this from an energy perspective. And the duster has disappeared. Someone even stole the cloth that was there. What am I supposed to do? Okay. Okay, let's look at all of this from an energy perspective. Let's plot energy on the y-axis and the processes as they happen on the x-axis. So we're gonna think about the energy of the system being in this state, the initial state, being in this state, and this state. So we'll have 4 distinct states to work with. So let's start with this guy. Say the solute alone and the solvent alone together have some energy, just some arbitrary energy. We don't need to be worried about what exactly it is. So this is just solute and solvent separately. Remember, all molecules we studied in the first chapter have attractive forces between them. at least they have dispersion forces between them, right? All molecules have dispersion forces between them. So it's safe to say that every molecule in the world is attracted, even if weakly, to other molecules. So this process of expanding solids, so what you're doing here is the solid particles were happy being attracted to each other. You've broken all of those attractive bonds here to separate them out. Does that take energy or give you energy? It takes energy, right? So if it takes energy, this state is higher in energy than this state because it took work to get there. So this is expanded solute and solvent alone. Similarly, we can, going from that to here, the solute hasn't changed, but the solvent, you separated the molecules yet again, that takes energy. And so you go up in energy again. This is expanded solute and expanded solvent. Correct? Expanded solute and expanded solvent. And then at the end, we are forming the solution. Now, solute particles attract each other, solvent particles attract each other, which is why it took energy to overcome that attraction. But here, you have solute particles nearby solute particles, you have solute nearby solvent particles, and you have solvent nearby solvent. All of those are attractive, right? So that will give you energy because you're now making them happy by bringing them closer. But it could either give you more energy than you had initially or less energy than what you started with initially. So when you get to the solution, you're going to be below both of these, that's for sure. But you don't know if you're going to be below where you were initially or if you're going to be above it. So now there's two options. You could either end up here, this is solution, or you could end up here. It should be in the same line, it doesn't matter. Say. Or you could end up here. Because now you've lowered in energy, the system gave you back some energy. If we forget about all the processes that happened, that took place to make this happen, and just focus on the initial state, this was the initial state, and the final state, you see that there is a net increase in energy. Yeah? This is initial to final. This is called the enthalpy of the solution. The difference between the final state and the initial state, that's the enthalpy of the solution, or enthalpy of dissolution. Same thing. It tells you how much energy it takes to take your pure solid, pure solvent, and pure solute and combine them to form your solution. And in this case, when the solution energy is higher than the initial alone energies, this is positive because you net gained energy. This is positive enthalpy of solution because you had to go up to get to the solution. However, if you're in the second case where the solution's energy is lower, then the solution's enthalpy is negative. This is the case of negative enthalpy of the solution. You know what that physically feels like? If you have a solution that forms with a negative enthalpy of solution, for example, take that solute in your hand, put a couple drops of water in your hand to dissolve it and rub it in, it will feel warm. Sometimes even hot. It could burn you. It could get that hot. You know those hand warmers, right? what's going on is it has two chambers. You have water and a solute that dissolves with a very high negative enthalpy of dissolution. So when you combine them, all that's happening is the solute in your hand warmer is dissolving in the water, releasing a big amount of energy, and that's what makes it warm. An example of this kind of solution where the enthalpy is positive is glucose dissolving in water. Have you ever had a tablespoon of just glucose powder? Anybody? You should try it. You know one of those candies that when you put in your mouth feels cold? Have you had one of those before? It's the same. So the reason why you feel cold is because glucose dissolves with a positive enthalpy of dissolution. So if you ever eat like a tablespoon of pure glucose, you'll feel your mouth get cold. Your mouth will literally get cold because it has a positive enthalpy of solution. So the dissolution happens along with the solution getting cooled down. Here, dissolution happens accompanied by heating instead. That's what negative and positive enthalpies mean. Okay. That's it. That's a simplified understanding of how dissolution happens. It's very basic, very natural arguments. Okay, ready to move on. Now let's talk about different ways to measure the concentration of a solution. Okay? That answers this question. You've got salty water. How salty is it? Very salty, moderately salty, right? Not that salty. These are qualitative terms. But if you want to put a number on it, if you want to put a number on the saltiness of water, you need to come up with some formulae. And that's what we'll be discussing. It's quantitative measurements of concentration. Concentration of solutions. So we're going to be talking about 1, 2, 3 measures of concentration. There's molarity. You should have seen this in Chem 1. There's molality, and there is mole fraction. Molarity denoted by capital M. Molality denoted by lowercase m, and mole fraction denoted by this symbol chi, CHI. Okay? These are just 3 of the many, many, many ways that exist of measuring this concentration of a solution. Molarity is defined as moles of solute divided by volume of solution in liters, or liters of solution. Little m, molality, is defined as the numerator remains the same, number of moles of solute, divided by kilograms of solvent. And lastly, mole fraction is defined as, so mole fraction, there's 2 kinds of mole fractions associated with any solution. There's only one kind of molarity and one kind of molality. But for mole fraction, you have to specify a mole fraction of what? So if you consider a solution that consists of two components, A and B, say A is solute, B is solvent, it doesn't matter. A and B are just two components of the solution, then the mole fraction simply means, mole fraction of A is simply moles of A. Anyone guess what the denominator is going to be? A plus B, total moles. Similarly, mole fraction of B is going to be moles of B divided by total moles. Total moles is A plus B. Moles of A plus moles of B. Yes.
Can you please repeat small m?
Little m? Yeah, moles of solute divided by kilograms of solvent. I'll figure this out at home, but does anyone know how to set the settings so that it doesn't sleep? I think there's a certain time factor going on. Yeah, someone had a question?
Can you repeat the mole fraction equations?
Which one's the mole fraction? Yeah, so mole fraction of A, chi sub A, would be moles of A divided by total moles. Mole fraction of B, similarly, moles of B divided by total moles. Yeah. So following this nomenclature, can you tell me what mass fraction of A would be? Yes.
Mass of A over total mass.
Over total mass. Good. Right, so fraction simply means one thing divided by total. Percent is the same, but you multiply by 100. So mole percent would be the same thing, but times 100. Mole percent of A, mole percent of B, and so on. Okay, so that's the nomenclature. Fraction versus percent. Great, so these three are the only things we'll be talking about. Notice the numerator in each case is the same. It's moles that goes on top, always. Usually, the question does not give you moles. It gives you grams. So how do you go from grams to moles? You divide by the molar mass. That's usually a side calculation. Liters of the solution are either given to you or sometimes milliliters are given to you. If you have 500 milliliters, what goes on the denominator here? Say that again? 0.5. Yeah, you want to convert it into liters, 0.5. Same thing here, you're usually given grams of solvent instead of kilograms, so be sure to make that conversion. Sometimes you're not given liters or kilograms, one of these, but you're given one of these and density. So if that happens, you're just going to use the density equation to figure this out. Start recording. Great. These cameras have an annoying 15-minute time limit, which is lots of annoying things. Great. Let's work out some examples. And I'll get you started with a fairly involved example, because you can do the simple ones on your own. Oh, by the way, one little fact about mole fraction is if you sum up the mole fraction of A plus the mole fraction of B, what do you expect? 1, right? Because fraction of one plus fraction of another gives you the whole thing. So mole fraction of A plus B is 1. That's just a little note to add. This is useful because you don't. It's not that useful. It's just a thing. All right. Concentration of solutions. Here's a question. Calculate the molarity molality, and mole fraction of a solution made by dissolving 100 grams. Has anyone worked as a barista here before? No? Yeah? Do you know what the ratios for simple syrup are? Have you made simple syrup?
Simple syrup, like from by mole, like from the powder and mix it up with the water.
Yeah. Do you know what the ratios are? Like, is it like half, half sugar, half water, or is it like?
Yeah, it used to be. It depends on like how like what's the volume of the water. Like if you take like 1 liter, right? Then you put like 4 or 5 packets. It depends on how like what's the measurement of the packets.
I see.
Yeah.
I see. Huh. My partner worked as a barista, and she used to tell me that simple syrup is, I think it is half.
It's half and half. Yeah, it's kind of half.
Yeah, half and half. Okay, so by dissolving 100 grams of sugar in 100 grams of, you know what? Let's not use regular water. Let's use heavy water. Just to make matters interesting. And I'll give you that the density of heavy water, what's the density of water? It's 1 gram per milliliters. Density of heavy water is going to be higher. Let's say it's 1.2 grams per milliliter. So we're making heavy syrup. Mildly toxic, but delicious. Yeah, because it has heavy water in it. Great. Okay. Yeah, that's all you have. Calculate the molality, and mole fraction of solution, blah, blah, blah. Great. Identify the solute here. Sugar, good. And the solvent would be heavy water. So first thing, let's calculate the number of moles of sugar. It's going to be 100 grams divided by its molar mass. Sugar is C12H22O11, but that's too much work. Let me look up what the molar mass is. Does anyone know the chemical name of sugar? Close. It's not glucose. Sucrose, yeah. Sucrose. Molar mass, yep. It's 342. .3 grams per mole. Cool. 342.3 grams per mole. That's about a 0.3 moles of sugar, I think. .292 moles of sugar. Great, I have my numerator, each case. Given that I have the number of moles, I have the numerator, which of these would be the easiest to calculate? Molality, or mole fraction, based on the given information? Say that again? Molality, right? Because I have the mass of my solvent. All I need to do is just to convert it into, yeah. So little m molality is going to be 0.292 moles of sugar divided by kilograms of solvent, which is heavy water. So what do I put on the bottom? 0.1. Convert it into kilograms. This will give you 2.92 moles per kilogram. Moles per kilogram is often abbreviated as little m. Okay? So 2.92 moles per kilogram is 2.92 little m. And you pronounce little m as molal, M-O-L-A-L. M-O-L-A-L. So instead of saying moles per kilogram, they just made up a new name. Little m, molal. Great. That's molality. Let's calculate molarity now. 0.292 moles go on top. Volume of solution needs to go on the bottom. How do we calculate our volume here? Density. And what's the definition of density? Mass over volume, correct? I want volume. So that would be mass over density. 100 grams divided by density is 1.2 grams per milliliters, which is 100 divided by 1.2. Mm-hmm. 83.3. So what would be the units here? Milliliters, right? Because the density was in grams per milliliters. Great. What would that be in liters? 0.0833 liters. Good. If you can't find a seat, just grab one from the other class.
So since we're using this for liters of a solution, right?
Yes.
So how come we just do the 100 grams and not?
Good. So we'll always use an approximation for the case of molarity. When you take, like, I don't know, a liter of water and you dissolve some sugar in it, does that really change the volume of the solution that much? No, right? A reasonable approximation to make is when you dissolve solute in a solvent, the volume of the solvent basically doesn't change. So what I'm saying is that the volume of the solution is approximately equal to the volume of the solvent. That's the approximation we're making. This is often easy to find because usually you're given the density of the solvent, not of the entire solution. But that's okay. Figure out the volume of your solvent like we did here and call that the volume of the solution because it will roughly be the same. So 0.0833 is our liters of solution, roughly. What is that?
3.505 or
Yeah, about 3.5 moles per liter. Moles per liter also has an abbreviation. It's big M. If this is molal, what do you think big M is? Molar. M-O-L-A-R. Molarity unit is molar. Molality unit is molal. Okay. Great. Let's calculate the last thing, mole fraction of each component. We already have the numerator. What else do I need to figure out for the mole fraction? Huh? What's my missing information for mole fraction? Say that again? Total moles. I have part of the thing for total moles. I have moles of sugar. Whose moles am I missing? Moles of heavy water. So moles of heavy water. It's 100 grams of heavy water. Mass of heavy water, D2O. Deuterium has a mass of 2. So 2 times 2, that's 4. 4 plus 16 is 20. Which is 5 moles.
What's the chemical equation?
D2O?
Oh,
Yeah. Heavy water, instead of H2O, hydrogen is the normal version of hydrogen. Deuterium D is the heavy version of hydrogen, and it's double the mass. Hydrogen has a mass of approximately 1. Deuterium has a mass of approximately 2. So that's 20 divided by 20, you get 5 moles. And so the last thing to do is to calculate mole fractions. Mole fraction of sugar will be 0.292 divided by 0.292 plus 5. Right, that's the total in the denominator. Similarly, mole fraction of D2O, 5 divided by 0.292 plus 5. Moles of 1 divided by the total. Okay. Any questions? Great. All right, so concentration of solutions, easy topic. It's just, usually plug and chug with some minor site calculations like we did here. Okay, cool. Now that we know how to measure the concentration of any given solution in 3 different ways, let's answer the question, just how soluble is something? So for example, if I have a given amount of water, I can't keep dissolving sugar in it, right? At some point, the dissolution will stop and the sugar will just start settling on the bottom. That's called the solution being saturated. Saturated is when you have reached the maximum solubility for a given solute, right? That's saturation. So solubility is defined as such. Solubility equals, it can be measured in a lot of different ways, but a common way is to do maximum grams of solute divided by either liters or milliliters of, no, it's liters. Liters of solution. That's solubility. It's how far you can push. It's the concentration of how far you can push in grams per liter. So, for example, the solubility of glucose is, let's check, sucrose, deciliter. Deci is 10, right?
Yeah.
Or is it 1 over 10? I think deca is 10. Deci is 1 over 10. Yep, 1 over 10. So the solubility of sucrose, sugar, is about 2,000 grams per liter of water. So you can dissolve as much as 2 kilograms of sugar per liter of water. If you ever see honey that crystallizes, you know, if something crystallizes, it means it's at the brink of saturation. Like it's like so thick that cool down the temperature just a little bit and it will reach its limit. Honey is about that much concentration of sugar to water. That's honey. Right? Honey is mostly sugar. And it's as bad as simple sugars. Yeah. Yeah, pretty much. The only thing that's different about honey is that it also has trace amounts of, you know, helpful antioxidants, this, that, other good things in it, like minerals and blah, blah, blah. But that's a tiny. So of the 2,000 grams per liter, maybe a gram or two will be your antioxidants or vitamins or minerals or something like that. Yeah, which is great, which is good, but if you're trying to avoid sugar, which is the main problem, honey is really not much better. Same thing with agave, all the sweeteners of your choice. They're all sugar. Sucrose. From a chemical perspective, but they taste better, I think. Cool, so that's solubility. So this formula puts a number on solubility. It's if somebody tells you what's the solubility of glucose, you can give me a number now. Now let's talk about some qualitative aspects of solubility. Some factors that solubility can depend on. Temperature is one, right? Hotter things tend to dissolve better. Temperature is one. And if you're thinking about dissolving gases in liquids, pressure would be another. Temperature and pressure. Let's talk about the solubility dependence on temperature and pressure for each of solid, liquid, and gas separately. So these are your solutes that I've given you. The solvent, for the purposes of this chapter, is always liquid. There exist solid solutions, but we're not going to talk about them in this class. A very good example of a solid solution where the solvent itself is solid is amalgams. Have you gone to a dentist and got a filler, like a silver filler? That's usually something dissolved in liquid mercury, which then turns into solid. So that's an example of a solid solution. They exist. But let's focus only on liquid solvents with these three different solutes. We've already established. So if you have sugar that's stubborn and it's not dissolving in your water, what do you do to the water? Aside from stirring it, heat it up. So increased temperature, solubility increases. So solubility and temperature go hand in hand for solid and liquid. Here's something you haven't tried: increasing the pressure on the system. That you haven't tried. It's not very practical. But if you did try that, you'll notice that pressure has no effect. Because the two components involved here are solid and liquid, and both of them don't really change volume when under pressure, right? So the effect is negligible at best. Nothing happens to solids when you apply different amounts of pressure. Nothing happens to liquids when you apply different amounts of pressure, roughly speaking. I mean, they do, squish a little bit, but not too much. So pressure has no effect for all practical purposes. But increased temperature, solubility goes up. Remember, solubility, we're talking about the limit of dissolution, right? Of course, you can always add more. That's not what we're talking about. We're talking about the maximum amount that can be dissolved. That goes up. That maximum limit goes up if you increase temperature. Liquids are weird because if two liquids are mixable, then they will mix in any ratio, right? For example, water and vinegar mix. If I have a tiny amount of vinegar and a lot of water, if I combine them, they'll mix. In the reverse situation, a lot of vinegar, tiny amount of water, they'll still mix. So here, it's not so much about solubility. Solubility is infinite. If the two solutions can mix with each other at any ratio, then they will always mix with each other at every ratio. So solubility is not the problem. The problem is, can the two liquids even mix or not? This mixing that I'm talking about, this has a more technical name. It's called miscibility. I think I'm pronouncing that right. It just means that are your two liquids able to mix with each other or not? Water and oil are not miscible. Have you heard of, especially those of you who use makeup products, micellar cleansers? It's just, the two things have been mixed. The cleanser has been mixed with water. It's dissolved. This is where it comes from, micellar. So miscibility. So the rule here is, if miscible, solubility is infinite. Yes.
What's miscibility?
Are the two liquids able to mix with each other or not? Yeah. That's what we call them. Yeah, that's the technical name for it. If they are not miscible, then the solubility is zero. They will never dissolve into each other. And what's the rule for miscibility? Likes dissolve likes. Which is to say, polar substances dissolve polar substances, and non-polar substances only dissolve non-polar substances. And polar, non-polar, we discussed that in the first chapter. Is water polar? Yeah. Is sodium chloride polar? It is ionic, which means it is polar. It's an extreme case of polarity. Do salt and water mix? Oh, we're talking about liquid miscibility. Okay. Okay, so water is nonpolar. Is ethanol polar? Alcohol. It is. If you draw the Lewis structure, you will see that it is. It's got to be polar. Do alcohol and water mix? Yes. Is gasoline polar? Gasoline, I'll give you a hint. It's a hydrocarbon. Hydrocarbons we learned are nonpolar. Gasoline and water don't mix. That's why when you have an oil spill, the oil floats on top of the water. They don't mix, causing all kinds of environmental problems. Great, so that's the rule here. Polar dissolves polar, non-polars dissolve non-polar. Lastly, let's talk about gas. Gas is very interesting when it comes to temperature and pressure. Both affect the solubility of a gas in a liquid. Let's talk about pressure first, because pressure is easy. If I increase pressure, suppose I have a little glass of water, I have carbon dioxide over the water, and then with the help of a piston, I'm pushing down on the gas. What do you think will happen? If I push down more, will more dissolve? Right? Because I'm literally pushing the gas into the liquid. So if you increase the pressure, the solubility goes up. That's the trivial case. What about temperature? Does solubility go up with an increase in temperature or decrease in temperature? For gases and liquids. Here's a hint. Have you had your water bottle and opened it on a hot day outside, and then it's like your water bottle is all bloated even though you didn't put any extra air at the beginning? Right? So for example, you fill up your water bottle on campus where it's cooler, it's nice. Then you go out on a sunny day, on a hot day, and then if you open your water bottle outside, like the bottle is all bloated. Have you experienced this before? No? Okay. I come from a very hot country, so yeah.
Happens every day over there.
Say that again?
Happens every day over there.
Say the video?
No, the thing.
Say that again? Oh.
Happens every day over there.
Oh yes, it does happen every day over there. It's like, yeah. In fact, that's how you get a sense of how hot it is. Heating up is bad for dissolving gases in liquids. If you heat up, the solubility goes down. Temperature increase, solubility goes down. Huh? Somebody ask why? Why? Yes, good question. So if you increase, the answer is not within the scope of this class per se, but we can make sense of it. If gases are just, moving around, they like to be crazy and wild, right? Liquids are more conservative. For the gas to dissolve in liquid, it needs to kind of calm down and slow down for it to stay inside the liquid. Otherwise, it will just keep bumping around and try and escape the liquid. When you heat up, temperature increase means that you're giving each molecule more energy. So it's going to go wilder. Its speed's going to increase. It's going to do a lot of crazy stuff, which makes it harder for the liquid to trap the gas that's dissolved in it. So more of the gas comes out instead. That's the reason. If you wanna convince yourself that this works, take 2 cans of soda, put one in the fridge, take it out, put it in the sun for an hour till it gets hot, and then open them up both. The one that was placed in the sun will have a bigger pop than the one that was in the fridge. Right? Hotter temperature, lower solubility. Bigger pop because there isn't as much dissolved carbon dioxide in your soda. A lot of it has come out of solution, is waiting to escape. That's why bigger pop. Okay, so enough talking about temperature and pressure dependence in solubility. It's very easy. Only thing to remember is that everything makes sense except gases with temperature. It sort of behaves the opposite of what some people might expect. Great. That's solubility. Here's a couple of favorite Alex questions that I've seen in Alex several times. Imagine a well whose walls are made of salt. Okay, so there's a crazy amount of salt present. And there's water in this well. And this well is old. I don't know, like 20 years old, whatever. First of all, what can you say about, so the salt on the walls has mixed with the water, right? So this is salty water. What can you say about the nature of the solution? Is it saturated? Is it unsaturated? What's going on? So basically the question is, has the water dissolved as much salt as possible? Yes, right? Because it's forever in contact with the salt. So the salt kept dissolving from the time the well formed until now 20 years later, all of the water inside is saturated. Yeah? But now imagine there's a temperature difference between the bottom of the well and the top of the well. I don't know, there's some volcano or something going on here. Let's make up a hypothetical. The temperature up here, say, is 20 degrees Celsius, and the temperature down here is 50 degrees Celsius. Imagine I go down there, take a little bit of sample of the water that's down here, I bring it back up to the surface, and I observe what happens to that solution. Here's a question now. When I bring it back to the surface and I examine it, will it be all just, solution state? Or will part of it be salt that's precipitated out and water mixture? So which of the two cases? Why?
Because when it was down there, it was at a higher temperature, so the solubility, the maximum was higher.
Yep.
And now that you brought it out, the maximum was not as high, so then you actually see a sediment doesn't dissolve anymore.
Correct. And the whole argument centers around the fact that this water was saturated to begin with. So it was already at max capacity at 50 degrees Celsius. The max capacity at 20 is less. So if you bring it up, definitely some of the salt will come out because it's past the maximum capacity for 20 degrees Celsius. Questions? Okay. Great. What if it was the other way around? I don't know, there's a giant iceberg or something here. I don't know how to make this realistic, but suppose this was 20 here, but 50 here. And I do the same thing. I take a sample of solution and bring it to the surface. Will it still be solution, or will it some salt precipitate out? In favor of solution? Precipitate. Well, the maximum capacity down here is still less than the maximum capacity up here. So we'll still stay in solution when you bring it up. In fact, you can add more salt after you bring it up, right? That's a favorite Alex question that I always like to ask. Great. Last part of the chapter is, I'll just give you a brief introduction and we'll start the full topic next time. The last part of the chapter is called colligated properties. Colligated properties. The idea is very simple. The properties of the solution are different from the properties of the solvent. when you take a pure solvent, if I take a huge thing of water and I add something to it, salt, sugar, whatever that dissolves, the solution that forms will have slightly different properties than the water that I started with. Right? So the solution has different properties than the solvent. We'll examine 4 such properties. We'll examine boiling point changes. Does the solution have a different boiling point than the solvent that we started with? Melting point changes, vapor pressure changes. Vapor pressure, I don't know if I discussed this in previous classes, but vapor pressure is very simple. Take some liquid, seal it. Whatever liquid you've taken keeps evaporating, but then it eventually will stop evaporating. So there is a buildup of gas in a sealed container. That equilibrium pressure, that's called vapor pressure. And it changes with how hot the environment is. Right? So vapor pressure is sort of like the native pressure of a liquid in a sealed container. It's always the same, no matter how big your container is, no matter how much water you take, it's always the same. So that's vapor pressure. If I put this in a sealed container, just water versus salty water, the pressures will be different. That's what I'm saying here. So the vapor pressure changes. And the last thing that we'll talk about is the osmotic pressure. This is something new to you, but the idea is very simple. Imagine this is how desalination works. This is how, well, again, going back to the country that I come from, it's a desert. There's no fresh water sources. So the only source to get drinkable water is to filter the salt out of seawater. This is how you do it. Take a big tank, simplified, of course. Put salty water in one of the chambers. And separate the other chamber, the 2 chambers, via a semi-permeable membrane. Semi-permeable membrane. What that simply means is it allows water to pass through but not salt. It stops the salt from passing through. So there's salt water here. There's this fine mesh that only allows water to pass through, and then it's going to get converted into water on the other side. Turns out, water just doesn't flow through this fine mesh on its own. You'll have to apply some pressure to make that happen. Okay? The pressure that you apply to make that happen is the osmotic pressure, roughly speaking. This was a rough example. Here's a better example. Imagine salt water there, and at the same height, you have pure water here. I don't know if you've learned this in like high school biology or something. Does anyone know what diffusion is? Osmosis? Water likes to go from high concentration to low concentration, right? That's osmosis. That's where the word I'm trying to explain where this osmotic comes from. So osmosis, any fluid likes to go from high concentration to low concentration. This is high, this is low. Water likes to seep through from the salt water to the pure water. Yeah, that's just osmosis. Now suppose you want to stop osmosis by applying a counteracting pressure on the pure water side. The amount of pressure that you need to apply to stop osmosis from happening, that's osmotic pressure. Okay? It's the amount of pressure that either osmosis exerts, that's one way of looking at it. The other way is, if you have salt water and pure water, you want to try and stop osmosis, the amount of pressure that you need, that's osmotic pressure. And it's always the same amount of pressure, no matter the size, shape, how much salty water you've got, how much pure water you've got, it will always be the same pressure. So we'll discuss, there's 4 equations corresponding to 4 of these properties. You'll see that the boiling point goes up, the melting point goes down for solution, vapor pressure can go up or down, and the osmotic pressure goes up. This makes sense because, boiling point goes up, right? You can use this fact in cooking. So what I'm saying is a pure solvent has a lower boiling point than the solution's boiling point. So adding salt to water increases the solution, the salty water's boiling point. So instead of cooking your food at 100 degrees Celsius, you're now cooking at 105. Higher temperature means faster cooking, right? So if you salt your pasta water, your pasta will cook quicker. Another example is if you saute onions or any kind of vegetables, add some salt, it'll cook faster. Because the oil's temperature is now higher with the salt in it than it was before. All right, we'll pick up this last topic next time, and I'll see you in a week. Oh yes, hold on for an attendance sheet. I'm sorry. Yeah, all good. I'm done.